Okay, great. So last time, we're going to continue on from last time where we're talking about compressed sensing and uniform compressed sensing, also known as for all compressed sensing, using RIP matrices. um, we talked about how to get RIP matrices. One of them is via JL, which is what you're showing on the piece that's due tonight. Maybe that's why attendance is so sparse today. Um, and we showed that if you had an RIP matrix, if you solve this linear program, also known as basis pursuit, you'll get a good approximation to the original vector x that was measured um, with this mixed L2, L1 error. So if you recover some x tilde, if you look at the L2 distance between x and x tilde, it's at most 1 over root k times the L1 norm of the tail of x. So that's what we saw last time. Another thing that, okay, so let me talk a little bit about what we're going to talk about today. So at the end of the day, you have to solve a linear program, right? This linear program has O of m constraints. Really m plus n, because if you want to express that L1 norm in terms of linear constraints, you need to add 2n more constraints, as we said last time. Basically, if you wanted to find yi to be the absolute value of zi, you're going to say that y is at least zi and y is at least minus zi, and then you're going to minimize the sum of the yi's. So you're going to have something like O of m plus n constraints, and you're operating in dimension n. You need to solve a linear program. That's going to take you some poly mn time, okay? Which is not incredibly fast. You know, imagine that you have an image, like did you all get the image I sent you of myself drinking from a baby bottle? Anyone out there?
Wait, what?
I sent an image of myself on the piazza, and I compressed it using the Haar wavelet basis. Did you see that? Did no one see this?
No.
Oh, that's very strange because I made it send immediately to email. But anyway, let me make sure that it's actually there now that no one knows what I'm talking about. I'm kind of surprised. So last week Thursday, yes, it's note 33 on Piazza. I said 2D Haar wavelet transform. So I sent an example of images. So images are not necessarily sparse in the standard basis, right? Let's say it's a grayscale image. So 0 is black and 255 is white. Okay, so anywhere in between is some shade of gray. So a typical grayscale image is not all zeros. It's not just a solid black image, right? An interesting image has objects and interesting things to see. Okay, so it's not really sparse. It's not approximately black. But if you do a change of basis, oh, by the way, I should say, if it's an n by n image, that's basically an n squared dimensional vector. Each pixel is a dimension, right? So yes, most natural images are not sparse in the standard basis, but if you do a change of basis, they typically, most natural images become sparse, and that change of basis is like, for example, the 2D Haar wavelet transform. So there's a description of what that is in the lecture notes. And I took a picture of myself from my first child's baby shower and playing some baby shower game, drinking from a baby bottle. It's a high def color image. There's not much black in it at all. And then I did a 2D Haar wavelet transform to it, and I put that on Piazza. That's note 33 on Piazza. I thought you all would have gotten an email, but I guess maybe a lot of people missed it or something. It didn't get sent out properly. I don't know, but I just checked. It is there. Anywho, you can see that after I run the Haar wavelet transform on it and get the new image, it's almost entirely black. Like you can barely, there's some edges you can see in the wavelet transform, but it almost looks like a totally black image. So it is approximately sparse. And that's true of like most natural images. Basically, when you do the Haar wavelet transform, there's some non-zero mass that corresponds to like boundaries between objects or like color gradients. But over large parts of the image where colors are pretty similar for adjacent pixels, it just, the change of basis makes that whole region black. So if you want, if you're interested in reading more about that, you can just look for it in the lecture notes. I talked about the Haar wavelet transform in the lecture notes, and look at the images on Piazza. I also put the code on Piazza. I wrote some code in Python, which takes any JPEG or PNG file as input and then spits out the image after applying the Haar wavelet transforms. You can take your own personal favorite photos, do a Haar wavelet on it, and see what you get out. And if it's a natural image, if it's not just like totally random colors, then it'll probably come out almost looking completely black. Okay. Out of curiosity, before I just said it now, have any of you ever heard of the Haar wavelet transform? Maybe I'll just quickly draw it here. It's in the notes, but just for your benefit. So here's an image, right? It's a square. It's n by n, and let's say n is a power of 2. The way I'm not going to describe what the actual basis vectors are because I don't think that's very enlightening. I'll just tell you how to convert an image from the standard basis into an image that's expressed in the Haar wavelet basis. Okay. So I'll describe an algorithm to do that change of basis. If you look at the code that I wrote that's on Piazza, basically it assumes that each pixel is a number, but of course in reality pixels are colors. But colors are actually just tuples of 3 numbers, right? There's an R value, a G value, and a B value. So what you do is you just treat your image as actually a 3n squared dimensional vector. So each pixel gives you 3 numbers, RGB, and then you just treat those as 3 different dimensions, and then you do this algorithm on each color separately. Okay. So anyway, so what's the change of basis? So what you do is so this is the input image, and this is the output image, which has the same dimension. It's also n by n. What you do is you divide up the input image into these 2 by 2 blocks. Okay. So there are basically n over 2 squared blocks, so n squared over 4 blocks, and each block has 4 numbers in it corresponding to the values of those 4 pixels. So let's call those A, B, C, and D. And what I'm going to do is in the output image, I'm going to divide the output image up into 4 big blocks that are each n over 2 by n over 2. And then they're going to be these 4 numbers are going to get transformed into 4 pixels here. So there's 1 pixel here, 1 here, 1 here, 1 here. Just because since it's the top left block, in the input image, it goes to the top left pixel in each of the output sub images. And what are each of these 4 numbers? So this one is going to be A plus B minus C minus D over 4. This one is going to be A minus B plus C minus D over 4. This one is going to be A minus B minus C plus D over 4. And this one is going to be A plus B plus C plus D over 4. Okay. So there's no information lost, right? So I took in 4 numbers, I did a full rank linear transformation and got out 4 new numbers. And you can, given the 4 output numbers, you can solve a linear system and reconstruct the original 4 numbers too. Okay, so there's no information lost here. This is purely a change of basis. And then what I do is I look at this top left part and I recurse. Okay. So just some intuition, if those 4 pixels, A, B, C, D, are not near the boundary of an object in your image, then probably nearby pixels are around the same color. That's the intuition for why this works well to compress things, right? Most natural images have few discrete objects, and within objects, the colors are very similar. So what that means is that what you kind of expect is that this pixel here, this pixel here, and this pixel here, basically all of these 3 regions, you expect to be very close to 0. Okay. And then when you recurse, you're going to end up doing the same thing. And then what you expect is now these 3 regions are they're still pretty close to 0, maybe not as close as before, because now technically these pixels are not adjacent. They're they're 2 away from each other. So you don't expect them to be as similar, but they're still pretty similar. So these 3 in the top left, these 3 in the top left corner in the next level recursion, these 3 regions are also probably somewhat close to 0. And then kind of as you recurse more and more, it kind of gets toward the top left corner, gets less and less similar to 0. It gets less black, but that area is smaller. So overall, most of the output image is going to probably look black. So this is called the 2D Haar wavelet transform. Of course, when you actually implement this, you can't actually divide by 4 because pixels have to have integer, RGB values between 0 and 255. So you have to, round it. You divide by 4 and round, but that doesn't really change that much. Okay. So it's not, so because of that rounding, it is not lossless. It is slightly lossy, but not too lossy. Does that make sense, by the way? Just the intuition behind like why this might be a good idea. Are people there testing? Hello. Yeah. Okay. So
Yeah.
Okay. So hopefully this makes sense. So anyway, check out the image on Piazza, and play with the code yourself and have fun. Okay. So in any case, how did I get here? Basically, if you look at that image on Piazza that I uploaded of myself, it was 2048 by 2048 pixels. So it was like 4 million dimensional in grayscale, but actually my image was not grayscale. It was actually full color. So there were RGB values. So it was more like 12 million dimensional. So imagine you're trying to solve basis pursuit on that image. It's a 12 million dimensional LP. Your algorithm is probably going to be really slow. Okay. So the question is like, how can you do compressed sensing with faster decoding times? And I should mention that, getting the number of measurements low is important because in some applications, the number of measurements actually is physical measurements by like a physical device. Like you're sitting in an MRI machine, and each measurement is the MRI machine making some measurement. Okay, so the more measurements it takes, the longer you have to sit in that machine. And that's actually a real problem for children, especially because children don't like to sit still, and you're supposed to sit still in those machines. So if you can get away with fewer measurements, it means the kid has to stay there for less time, which is more practical for doctors to execute. And in fact, we have faculty here who work on compressed sensing for MRI. One of them is in the EECS department. It's Professor Mickey Lustig. I don't know if any of you have taken a course with him, but we actually have another professor in bioengineering. I'm forgetting his name right now, but he also does kind of MRI stuff as well. So these are things that really do get used. In any case, so yes, we want low measurements, but we also want low decoding time because, again, in this image scenario, you have some 12 million dimensional vector, like an image, a high-res image, and I can't afford to spend n squared time to decode if n is 12 million. Okay, that's too much. So people realized this pretty early in the compressed sensing literature, and they tried to come up with other recovery schemes that were faster than solving basis pursuit, faster than solving a linear program. So we're going to talk about that a little bit today. So iterative methods for compressed sensing. I'll call it decoding, meaning given pi x plus e, want x tilde fast such that x tilde is roughly x. We didn't talk about this e last time. This is fast. Sorry, my handwriting is terrible. But again, e. I'll do the analysis including e because it actually doesn't really change the analysis by much. It doesn't make it that much more complicated. But this is post measurement noise. So as you might imagine, I have some physical device like a telescope, like an MRI machine. It's doing measurements on a signal, okay? But what you read from the machine is not an exact real measurement, right? The device itself has some noise, so it might only measure what you're trying to measure up to some error of 0.001 or something, right? So that difference between what you measure and the true value of pi times x, I'm calling that E, which is the post-measurement noise. Okay. And there are a lot of iterative algorithms. There's like cosamp. There's iterative hard thresholding. There's sequential matching pursuit, and they're expander expander matching pursuit. There, I could go on forever. Honestly, there's a whole industry of papers in this area, sub area. So let me not continue. But just to give you a flavor of it, today I'm just gonna focus on one of them. So, and this analysis that I'm going to show you is due to Blumensath and Davies in 2009. So what is the kind of guarantee that, well, first let me write what the algorithm is. Iterative hard thresholding. It takes as input y, which is equal to pi x plus e. And also pi, which is the actual pi is going to be some RAP matrix that you're using to do the measurements. And it's an iterative algorithm, so it starts off with an initial guess of x, which I'll just guess initially as 0. And then it says for t equals 0 to capital T, what I'll do is I'll do some kind of update rule. I'll say at plus 1 gets to be xt plus pi transpose y minus, I think something like pi xt. And then xt plus 1 gets to be, they call it, so it's called iterative hard thresholding because it's an iterative algorithm that keeps doing hard thresholding. What is hard thresholding? It's this operator. HK is what's called the hard thresholding operator applied to AT plus 1. And this is, this is also known as, the head vector. So take the vector AT plus 1 and zero out all but the top k coordinates in magnitude. And then now you return, xt plus 1 or something. And I guess you have to give it as input like t, like how long do you want to go for? Okay, so I think that's a very simple algorithm to write down. Any questions about what the algorithm is doing, or like anything question about the pseudocode? Okay, good. And and just some intuition, what should you be thinking here? Intuitively, for all these for all these JL matrices, RAP matrices, etc., pi is a matrix such that pi transpose pi is supposed to be in some way an approximation of the identity matrix, right? If you think about JL, right, pi x L2 norm squared should be roughly x L2 norm squared. Okay, but what is x L2 norm squared? That's x transpose x. What is pi x L2 norm squared? That's x transpose pi transpose pi x. So basically there's a pi transpose pi in the middle. And wouldn't it be great if pi transpose pi was the identity matrix? Then, we would preserve the norm exactly, okay? And and the name of the game in a lot of these matrices that we design, whether it be RAP, whether it be JL or whatever, is come up with some distribution such that pi transpose pi is the identity and expectation. And not only is it the identity and expectation, but it preserves whatever you want to preserve for the application at hand with high probability. So the kind of the intuitive picture to always keep in mind is you should always think that pi transpose pi is trying to be like the identity matrix. So if you look at this code, what is it saying? Look at y. Ignore the e for now. E is this post-measurement noise. Forget about that. Y is pi x, right? Okay. So pi transpose y is pi transpose pi x. Pi transpose pi x is supposed to be roughly x because pi transpose pi is supposed to be the identity. Meanwhile, pi transpose pi xt is supposed to be roughly xt. So what AT plus 1 is trying to be, AT plus 1 is trying to be xt plus x minus xt. And lo and behold, the xt's cancel, and what you're left with is x, which is great. You're trying to converge to x, okay? And we end up doing this hard thresholding operator before going to the next iteration. And the reason we do it is, we need to pi, we need to at some point use the fact that pi has a certain property. The property we're going to use is the restricted isometry property. And if you keep applying pi to non-sparse vectors, then it's hard to say anything in the analysis because RIP matrices only work well on sparse inputs, right? So if you notice here, we're applying pi to xt in the for loop, right? Y minus pi xt. Well, xt is k-sparse. So we can hope to reason about pi times xt because it's pi applied to a sparse vector. And you know, that's kind of, you're going to see it now when we actually do the analysis formally, but that's why we keep doing this hard thresholding operator, is to keep making sure that we're always applying pi to something that's sparse so that in the analysis we can actually reason about it. Okay. So good. Does the code make sense and does the intuition make sense before we actually do a formal analysis? Okay, so good. Let's get on to a formal analysis then.
Can I ask a question?
Okay.
So are we in the context where like even trying to just solve like lasso is too expensive?
So lasso is like L1. It's L1 minimum.
Penalize least squares.
Right, but
because I was under the impression lasso was very commonly used for these sparse problems.
But when people solve lasso, I mean, one way to look at all these iterative algorithms is that they are solving basis pursuit. They're just not solving it via an off-the-shelf linear programming algorithm. They're solving it using some iterative algorithm that specifically guarantees that, you know, that works for specifically basis pursuit, but not general LPs.
Okay, I see.
Yeah, I don't know if that answers your question, because even lasso, I mean, if you just write it as it, you know, I think people don't solve lasso just by using an off-the-shelf like convex programming algorithm like ellipsoid or something, right? They use iterative algorithms as well.
Right. Yeah. Mm-hmm.
Right. So I mean, I think it's a similar story.
Okay, I see. Thanks.
Yeah. Okay, so let me write the theorem down and then we're going to prove it. So theorem, and this is due to, I said, Blumensaft and Davies in 2009. Sorry. Okay. So the theorem says, suppose pi satisfies epsilon comma 3k RIP. Okay. For epsilon less than 1/4 times some constant that's going to come up in the analysis, similarly to when we're analyzing basis pursuit. Then for all capital T going equal to 1, we have a bound x t plus 1 minus x L2 norm is bounded. So this less than twiddle means up to a constant factor. Your error is going to be 1/2 to the t times the L1 norm of x. And you know, if this term right here is coming from the fact that basically it's because our initial guess for x was the 0 vector. We chose x0 to be 0. If somehow magically you were able to get a better starting point, this could also be improved. But you know, it's exponentially decaying anyway. Plus x tail k L2 norm, okay, plus 1/√k x tail k L1 norm plus the norm of E. So in terms of what here is new compared to what we saw in the analysis of basis pursuit, you know, we didn't have, of course, the straight, you know, solving the LP didn't have this term that comes from the iteration. We also didn't talk about this when we talked about basis pursuit, just because we didn't talk about post-measurement noise. But that has to be there, right? Like if there's a post-measurement noise of norm alpha, like you're not, I mean, that noise could have been anything. So you know, you're gonna have some kind of dependence on alpha in your error bound when you do recovery. So, and also I guess We didn't have this term either, right, when we talked about basis pursuit. But I want to just show you that that term actually is morally bounded by the L1 term. And the reason is just due to shelling, okay? So let me just show you that. So lemma. Let's look at x tail 2k, L2 norm. I claim that that's at most something like 1 over root k times x tail k. That, I mean, k here is anything. It's just, this is just a general fact about vectors. And, in particular, that means that, what that means, for example, is that this part here is at most 1 over root k over 2 times x tail k over 2. So, up to changing k by a factor of 2, it's dominated by the other term anyway. If you wanted to have error that was k and not k over 2, just use an RIP matrix that's actually 6k RIP. Okay, and then you would get, then you pretend that your k was actually 2k. So what's the reason for this? So proof. Let's just, without loss of generality, I'll just pretend that the entries of x are sorted in descending order. So x1 is at least x2 is at least x3, etc. And then now I'm going to, just like I did in previous proofs, divide up the entries of x into blocks. So this is, I'll call this like S1, has size k, and then S2 has size k, etc. Okay. And then now when I look at x, actually, here, so I said 2k, so let's actually make it 2k. Okay. Then if I look at the L2 norm squared, x tail 2k L2 norm squared is equal to the sum j goes from 2 onward to, I guess, roughly n over 2k of x sj L2 norm squared. Okay. And now I can say that this is at most the sum j goes from 2 onward of, so the L2 norm is at most root dimension times the L1 norm by Cauchy-Schwarz. But, xsj is actually a sparse vector. It only is 2k sparse. So instead of paying root dimension, you only have to pay root 2k. So this is at most root 2k times the L1 norm, xsj L1 norm, and then it's squared. And then now what I can do is I can compare each element. So, okay, so what is this? Like, let's look at, what am I doing? I'm summing up the absolute values squared of like this thing plus this thing plus this thing plus this thing. Each one of these things is at most the average in the previous block. That's shelling, right? So this is at most root 2k, and now this is Cauchy-Schwarz. This is shelling. The sum j equals 2 onward of how many entries are in XSJ? There are 2k of them. So 2k times each entry there is, well, let me write it like this, 2k times XSJ L infinity norm squared. And what can I say about the L infinity norm? The L infinity norm is at most the average of the, it's at most the L1 norm of the previous block divided by k. In other words, it's at most the average of the previous block. So, okay, so this is not quite shelling yet. Now let me do shelling. So now let me say shelling. So this is shelling. Root 2k times the sum, now j goes from 1 onward of 2k times xsj L1 norm over k, and then the whole thing was squared. Okay. Good. So now, where are we at? So this is a k, and the denominator is a k squared, and then there's a root k out here. So we have k root k in the numerator and a k squared in the denominator. So this is equal to 1 over 2 root 2 over k, I guess, times the sum j equals 1 onward of xsj L1 norm squared. And then now let's just square root the whole thing. So square root this, square root this, square root this, square root this. Square root this. I feel like, though, this should have been a square root k, right? But yeah, and now the point is just like root a plus b is at most like root a plus root b. So this square root of the sum, I can just apply the square root term-wise, and then I'll get the sum over j of xsj L1 norm, which is just, oh, okay, I see now what yeah, okay. So very minor thing that I should say. Actually, what I'm going to do is I'm going to make in my definition of the SJs, I'm actually going to get rid of, I'm not going to make it 2k, I'm going to make it k. Okay. And then now, since I have x tail 2k, I'm starting from j equals 3 onward. Okay. And then now this is not a 2k, this is just a k. So now I feel happier. And now this is not a 2k, this is a k. Sorry for the confusion. So I don't have all those 2's everywhere. So good. So now I have the L1 norm over root k. And this j goes from 2 onward. So I actually have x tail k. Sorry for the confusion about the 2's, but does this make sense? Do you have any questions? So, okay, so good. So now let's just try to prove the theorem. Okay, so as I defined it, I said at plus 1 is just defined to be xt plus pi transpose y minus pi xt. Where I remember right, if I said that y is equal to pi x plus some post-measurement noise. That's the definition of y. And let me also define rt plus 1, or rt plus 1. Let me define that to be x minus xt plus 1. So this is the the residual. So our goal is to bound, right? If you look at the theorem statement, our goal is to bound the norm of the residual. Right? That's what's on the left-hand side there. Okay. So let me make some definitions. So some notation, actually. So first of all, let me define S. Okay. Another thing I want to say too, which is maybe also worth saying in the beginning. Without loss of generality, I can assume that S is exactly K sparse. Okay. Why is that? Because now that we have post-measurement noise, I can write X. The reason is as follows. I can write X as being X head K plus X tail K. Okay. And then I'll just pretend like this is really X. And then this is something else. But notice now pi X plus E is equal to pi X head K plus pi X tail K plus E. And I'll just treat this entire thing as post-measurement noise. Right? And what's the guarantee that the algorithm is giving us? The guarantee that the algorithm is supposedly giving us is that our final error in recovery has the norm of E in it, and it also has the norm of X tail K in it, the L2 norm of X tail K. So, this is my new like, I'll call it E tilde. E tilde is my new post-measurement noise. So if we're getting error that depends on the norm of E tilde, well, the norm of E tilde by triangle inequality is at most the norm of E, which we're happy to have anyway. We don't mind having the norm of E in our recovery error, plus the norm of pi X tail K. What can I say about the norm of pi X tail K? How can I control that?
Isn't it 0, right? Or very small?
We don't know that, right? I mean, why do you say 0?
Wait.
So X tail K is like it's like X minus its head, right? So it's like take the best k-sparse approximation of X, and then subtract it off. That's X tail K, and pi is this RIP matrix that has 3k RIP. First, let me ask you: is X tail K, is it sparse? Is it a 3k sparse vector? It's not, right? I mean, it could be anything. We don't know how sparse it is. But the key thing to realize is kind of the thing that's more important about RIP is that not only do you preserve norms, not only do you like not blow up the norm a lot, but you also don't shrink the norm a lot. Like the norm of pi x, if x is sparse, the norm of pi x is at most 1 plus epsilon times the norm of x, but it's also at least 1 minus epsilon times the norm of x. Okay, so X tail K is not sparse, so we can't say that pi doesn't shrink its norm too much. But we actually don't, in this context, we actually don't care whether pi shrinks its norm. If pi makes its norm become 0, great. That's less error for us because we're trying to bound the norm of E tilde right now. All we want to argue is that pi doesn't increase the norm of X tail K by much. But in fact, that's just true for any RIP matrix by the triangle inequality. Okay, so take any RIP matrix, give it any vector which is not necessarily sparse at all, and I claim that pi can't increase its norm by much. Why not? Because this thing is the same thing as pi times the sum j goes from, let's say, 2 onward to n over k of x sj L2 norm, right? So S1 is the largest k entries in magnitude. S2 is the next largest k. X3 is the next largest k, etc. So X tail K I can write like this. And then this is at most the sum over j, at least 2, of the norm of pi xsj. Okay. And ta-da, now I can use RIP because these are actually sparse vectors. This is at most, by the definition of RIP, let's say square root of 1 plus epsilon. Square root just because the way I defined RIP, it preserves the squared norm by 1 plus epsilon. So this is not the square norm, it's the square root of the squared norm. So root 1 plus epsilon times the sum over j bigger than 2 of the norm of xsj. And then now how can I finish this off? Right, I can do Cauchy-Schwarz. Cauchy-Schwarz says that this is at most root 1 plus epsilon of the sum j bigger than 2 of xsj squared square root. That's Cauchy-Schwarz. And this, by definition, is just the tail vector, the norm of the tail vector. So this is equal to root 1 plus epsilon times the norm of x tail k. Does that make sense? So I guess one life lesson to keep in mind is this fact that if you just don't want to blow up norms, you don't care about you don't mind shrinking norms, you just don't want to blow up norms, then RIP gives you that even for non-sparse vectors, just because you can do triangle inequality like this. So yeah, so good. So basically what I'm saying is if I just pretend that x is actually x head and throw pi x tail k into the post measurement error, just pretend like it's post measurement error, then if my new post measurement noise is e tilde, the norm of e tilde is bounded by the norm of e plus roughly the norm of the tail, which is within my tolerance for the kind of error I'm willing to have in the theorem statement, right? I have both of those terms on the right-hand side anyway. So from now on, for the rest of the proof, I'm just going to assume that x is actually its head, meaning that x is actually a k-sparse vector.
Sorry, I have a question. When you apply Cauchy-Schwarz, why don't you pick up a factor of like square root of d over k?
It's let's see. So, oh wait, that's a good. Actually, you bring up a very good point. I should pick up something, right? Oh, you know what? Okay. Yeah, that's not what I should have done. Here's what I'll do, and here this will actually fix it. I can make my life even. I am going to do Cauchy-Schwarz, but I'm going to do Cauchy-Schwarz to pick up an L1 norm. So this is at most. So this is a k-sparse vector. So I can say it's at most root 1 plus epsilon times the sum, right? L2 is at most something's a little off here. So I wanted to say this is at, so L2 is at most L1. Yeah, I think what I need to do is I need to shell. Sorry, I thought I. Oh, okay. Wait, let's see. Here's what I can do. So okay, so crap. Yeah, you're right. You're right that that's not actually what I should do. But I think what I can do is, if instead, sorry, I don't know how I missed this. So if I do something like x had 2k tail 2k, and here I have a 2k and a 2k, I think basically what I can do is I can shell and then compare this to the L1 of the previous block and get something like L1 over root k. And I think if I do this properly, I can get something like, I can prove that this thing will end up being something like x tail k L1 norm over root k via shelling. So let me, sorry about that. Yeah, I think I'll fix that in the notes, but you can definitely fix this and get an error term that is bounded by this. I think you're right. It's not going to be bounded by this. It's going to be bounded by something like this. Sorry about that. I'll fix that in the notes though. Does that roughly make sense as to what I'm trying to do there?
Yeah, I think it's similar to the lemma, except after you apply pi.
Right. Yeah. Very good. Yeah. Okay. Good. So so anyway, from now on, I'm just going to so I guess maybe it's 2k, but I'll just pretend it's k. So from now on, x is k-sparse. Okay, and then let's run this argument for a k-sparse x. Okay, so let me do some more definitions. So from now on, x is actually sparse. And I'm going to make some definitions. So S star is going to be the support of x, so that the size of S star is at most k. And then I'm going to say ST is just defined to be the support of XT. So again, this has size at most k as well, because we did the hard thresholding operator. And then BT is going to be defined to be ST union S star. So the size of BT is at most 2k, because I just took the union of two sets, each one has size at most k. Okay, so let's try to understand a bit. Let's try and prove a bound now on the norm of the residual. Okay. That's what we're after. That's what the theorem is saying, that's bounded. Okay, so bounding the norm of RT plus 1. Okay. So good. We're going to do some triangle inequality. So RT plus 1 L2 norm, by definition, is equal to x minus xt plus 1. Okay. Which now, x is, x and xt plus 1, both of their supports are a subset of bt plus 1. So this is equal to the norm of xbt plus 1. I'll just write it like this, bt plus 1 minus xt plus 1 bt plus 1. Okay. And then now I'm gonna insert the vector a before I did the thresholding, and I'm gonna subtract it into triangle inequality. So this is at most xbt plus 1, okay, minus at plus 1 bt plus 1 plus abt plus 1 minus xt plus 1. Okay. Now, what is, I claim that, first of all, I claim that this is smaller than this. So the inequality goes something like this. The second summand is smaller than the first summand. So why is that? Right. When you apply the hard thresholding operator, you get the best k-sparse approximation of the input. So xt plus 1 is the hard thresholding operator applied to at plus 1. So meanwhile, x itself, remember, x is k-sparse, right? From now on, we're assuming x is k-sparse. X is some other k-sparse vector. So, it cannot be as good a k-sparse approximation to A as xt plus 1 is. Okay. So the left summand is bigger. So this is at most 2 times the left summand. Does that make sense? Okay, so now how do we bound that? Okay, so now let's expand out what A actually means. Okay, and from now on, I don't want to keep writing BT plus 1. So from now on, B is BT plus 1, and B prime is BT. Let me get rid of all the, that's confusing. Okay. So this is 2 times xb minus at plus 1b. So let's expand out what A actually means. Okay. So this is equal to 2 times xb minus, I think it's like xtb, okay, minus pi transpose b, y minus pi xt. And then now let's also expand out what y means. Y, remember, y is equal to pi x plus e. Okay. So if you expand that out, y is equal to pi x plus e. So you have a pi x minus pi xt. That's just equal to pi times rt. And then you have an e that showed up in there. So this is equal to 2 times xb minus xbt, which by the way is also known as, I guess I can simplify that too. xb minus xbt is also known as rt projected to be. So this is rt projected to be minus pi b transpose, and then y minus pi xt is equal to also pi rt. Okay, plus e. Okay, does that make sense? And now, good. RT is fully supported on B prime, right? Well, actually, let me write RT like this. I'm just going to write RT is equal to RTB plus RT B prime minus B. Okay. In reality, oh yeah, good. I can read that because I know what is RT. RT is x minus xt, right? X has all its support in either B or B prime because both of them contain S star, okay? And xt has all its support in B prime. So B union B prime contains everything. I mean, in fact, just B prime does. So now I can write this as, this looks like a mouthful, 2 times RBT minus pi B transpose pi B RTB. Okay. Minus pi B transpose pi B prime minus B R B prime minus B T. Okay. Minus pi B transpose E. Does that look right? So let me move this over to the next slide because this is getting to have a lot of symbols. So we had that, and then so what do we start off with? RT plus 1. We said at the end of the day it's at most 2 times RBT, okay, minus, I said pi B transpose pi B RT minus pi B transpose pi B prime minus B RT B prime minus B and then I think I had a minus pi B transpose E. Okay. So this is the same thing as, I'll say, identity B, the identity matrix restricted to the columns in B, minus pi B transpose pi B times RBT. Okay. So I can write that this is all at most. Let me do triangle inequality now. 2 times the operator norm of that matrix plus 2 times the norm of the operator norm of this matrix times the norm of the vector, and then plus the operator norm of this matrix. Well, sure, pi B transpose E. Operator of this matrix times E. Okay, so I just did some triangle inequalities, and I also wrote that the norm of AX is at most the operator norm of A times the norm of X. Okay, does that make sense? So now let's just go through these one by one. Just by definition of RIP, okay? Remember now, this matrix pi has 3k RIP. Okay. So this thing is at most epsilon. That's just the definition of RIP. Okay. This thing also, we've used this lemma multiple times so far. We used it once when we were analyzing basis pursuit. We used it once when we were analyzing the Kramer-Ward theorem for FastJL. If you look at pi sub A transpose pi B, where A and B are disjoint sets, and their union has size at most the RIP level of pi. So here, pi is 3k RIP. How big is the union of B and B prime minus B? The union has size at most 3k. So by a lemma that we've already seen twice in class so far, this thing has operator norm at most epsilon. And if you don't remember the intuition for that, we basically used the parallelogram rule. We said, look, let's say that you have two sets of columns A and B, which are completely disjoint. Okay. And let's say X is fully, let me give two different letters. Let's say that we have vectors Y and Z. Y is fully supported in A, Z is fully supported in B. Y dot Z is 0, right? So pi Y times pi Z, or pi Y dot pi Z, should be close to 0 by parallelogram rule. As long as pi preserves the norm of Y plus Z and Y minus Z, you can do some parallelogram rule and expand and cancel similar terms, and you'll get the dot product has to be preserved up to additive error epsilon. The original error was 0, so the new error has to be at most epsilon, right? The original dot product was 0 because they have disjoint support. So the new dot product has to be at most epsilon, which implies that the operator norm of pi A transpose pi B is at most epsilon. So as long as the sets are disjoint support and the total union has size at most the RIP level of the matrix pi, they're good to go, and the operator norm is at most epsilon, which is true for us. Okay. So this matrix has operator norm at most epsilon. And also, again, pi B transpose pi B is close to the identity and operator norm. It's within epsilon of the identity and operator norm. What does that mean? It means that all the singular values of pi B transpose pi B are between 1 minus epsilon and 1 plus epsilon. Okay. So if you know that all the singular values of pi B transpose pi B are between 1 minus epsilon and 1 plus epsilon, what does that say about the singular values of pi B transpose? Well, first of all, they're the same as the singular values of pi B. What are the singular values of pi B? If I tell you the singular values of A transpose A, what are the singular values of A in terms of the singular values of A transpose A?
Square root.
Yeah, they're just the square root. So you know that pi B transpose pi B has all its singular values between 1 minus epsilon and 1 plus epsilon. So that tells you that the singular values of pi B transpose have to be between root 1 minus epsilon and root 1 plus epsilon. So in other words, they're still close to 1. So in summary, this whole thing is at most 2 epsilon. I think there's also a 2 out here too. I forgot the 2. 2 times, yeah, so there's right there. It's 2 epsilon RBT L2 norm plus RB prime minus B T L2 norm. Okay. Plus 2 times the square root of 1 plus epsilon times the norm of E. Which, this is anyway, now I can ignore this. So this is at most, let's say 3 times the norm of E. I'll be able to slot E. As long as epsilon is small enough. Okay, what can I say about this? So this is just this is just gonna be like the AMGM inequality. So notice that, let's just give these names. Let's call this alpha, and let's call this beta, right? What do I know? Alpha squared plus beta squared in this case is equal to, because they have disjoint support, this is equal to RB prime T L2 norm squared, right? Because it's equal to RB squared plus RB prime minus B squared, but those are disjoint support, so the squared norms just sum up. Okay, so let's just call this, yeah, so okay, so good, it's something. But we don't have alpha squared plus beta squared. We have alpha plus beta. So what can I say about alpha plus beta? I claim that this is just a fact about numbers. Alpha plus beta, I claim, is at most square root of 2 times alpha squared plus beta squared. So, okay. So in other words, if you look at this sum, what I'm saying is that this thing is at most square root 2 times the norm of R B prime T. Okay. So why is this fact true? You just square both sides. So this is the same thing as saying alpha squared plus 2 alpha beta. So this is the same thing as saying that this is true. Alpha squared plus alpha beta plus beta squared is at most 2 alpha squared plus 2 beta squared, which is the same thing as saying that alpha beta is at most alpha squared plus beta squared over 2 if you just rearrange things. But this is true by the AMGM inequality. Right? Arithmetic mean is at, oh, is it going the wrong way? Yeah, the arithmetic mean is at least the geometric mean. So the arithmetic mean between a squared and b squared is at least the geometric mean between a squared and b squared, which is AB or alpha beta. Okay. So in summary, what we have is that RT plus 1 L2 norm up there is at most 2 epsilon times 2 root 2 epsilon, because there's a root 2 there now, 2 root 2 epsilon times RB prime T L2 norm plus 3 times the norm of E. And remember what I said that epsilon is small. Epsilon is less than 1 over 4 root 2. Right? That was my condition. Now you see why. So now if I go back to where I was and use that fact, this is at most 1/2 times the norm of RT B prime L2 norm plus 3 times the L2 norm. And by the way, RTB prime is also known as RT. You don't need the B prime there, right? Because what is RT? RT is X minus XT, right? So X has its support contained in B prime by definition. By definition, B prime contains S star, right? B prime is just BT, which contains S star. Okay, and B prime also contains ST, so it contains the support of XT as well. So RT is fully supported in B prime, so I can just drop the B prime. Okay, so we're getting some kind of exponential decay. RT plus 1 has norm at most half of RT plus 3 times E times L2 norm. So what you can show, so if you can do this out formally by induction if you want, but basically what you're getting is that the claim can prove by induction. So if you just look one level deeper, so you know that. So what do you know? You know that R0 has norm equal actually, because R x0 is just the 0 vector. So this equals the norm of x. Meanwhile, R1 we said is at most a half times the norm of x plus now 3 times E2. Let's just do one more. So what about the norm of R2? This thing is at most a quarter times the norm of x plus 3 halves times the norm of E2 plus 3 times the norm of E2. So, you know, eventually what you're going to get is RT is going to be like at most, the norm of RT is going to be at most 1 over 2 to the t times the norm of x plus 3 times, you know, 1 plus a half plus a quarter plus whatever times the norm of e. Okay. So what you're going to get is RT plus 1 is actually at most something like 1 over 2 to the t plus 1 times the norm of x plus, you know, at most something like 6 times the norm of e. And remember, this e was really, you know, e tilde. So when you bound that norm of e tilde, that's when you get, you know, the dependence on like 1 over root k times the norm of x tail k. Okay. So that's pretty much it. Questions about this analysis? Okay. Any questions? Okay, so if there are no questions, we still have 15 minutes left. So what I'm going to do is I'm not going to do a full analysis, but I'll tell you about, you know, another kind of very different way of coming up with measurement matrices that also gives you some kind of decent recovery results. And it's based on the notion of an expander. So just out of curiosity, who here in the audience knows about expanders? Anyone?
Yeah, I think a few of us are thumbsing up in the.
Oh, okay, sorry, I can't see the chat, so give me 1 second.
I saw 2 thumbs ups, but I don't know if I saw all of them.
Okay. Sorry.
3 thumbs ups.
Oh, okay, good. Okay, good. So first of all, another method for compressed sensing, and there are also iterative recovery algorithms that correspond to this method. So instead of choosing pi to be like a random Gaussian matrix or something, what we're going to do is we're going to pick pi to be the adjacency matrix of an unbalanced bipartite expander. Okay, so expanders. And I'm going to specifically talk about bipartite expanders. So what we're going to do is we're going to have it's going to be imbalanced. So here we're going to have n vertices. And here we're going to have m vertices. Hint, hint, m is going to be the number of measurements in our matrix, and n is going to be the coordinates. Let's call these v. And we're going to have a left regular graph that's d left regular. So every vertex here has out degree exactly d. So G is equal to UVE. It's bipartite. And it's D left regular or left D regular. I don't know what the order to say those things in. So what does it mean to be an expander? So we're looking at so-called lossless expanders. Okay. So if you look at, let's say gamma is the neighborhood function. Take S, which is a subset of the left side, and look at gamma of S. So gamma of S is the set of all things which are neighbors on the right. Okay. Now, what's the biggest this could possibly be? You know, the biggest this could possibly be is at is at most D times the size of S, right? If every single edge coming out of S, there are no collisions, they all go to different vertices on the right, the most you could possibly get is D times S. If it gets at least 1 minus epsilon times D times S, if it gets this for all subsets S of U such that the size of S is at most K, then we call G let's call it a K epsilon D expander. So that's the definition of a bipartite expander. For those of you who have not seen expanders before, you can also talk about it. Does you can make the same definition for non-bipartite expanders as well. Basically, if you take any subset of vertices, you just want to say that if you look at its neighborhood, it expands a lot. Okay, so for example, something that would not be an expander would be a bad example would be something like this is the canonical bad example. What's called a barbell graph. So imagine that these are like very tightly connected graphs, but there's like one very loose. Is that what I wanted to say? Actually, no. Let me just draw. Let me not be too. Fancy. Here's a very simple bad example. Okay, so a very simple bad example is so let me just divide up the right hand vertices V into like 3 groups of size 3, and let's say that each vertex on the left is connected to one guy in each bubble on the right. So like this is all V, and this is U. And let's say this guy's connected here, here, and here. What I don't want to happen is I don't want this guy to also, let's say, go to the same exact places. And maybe the next guy also does that. This would not be an expander, because if you look at a small subset on the left, like if you just look at these 2 vertices, for example, you want that, the maximum vertices on the right they can hit is 6, because each one hits 3. And if they're disjoint, they'll hit 6. But here, the union of what they're hitting is only 3 because they overlap too much. So an expander is a graph where that doesn't happen. If you take any subset of vertices on the left, they don't overlap too much in terms of who they hit. Okay, there can be some overlap because that's why you have that epsilon loss there, but it shouldn't be too much overlap. Okay, so now you can show that good expanders exist. So theorem, there exists expanders with parameters what's it called? K epsilon D for M being something like O of K over epsilon squared log N over K, and D being O of 1 over epsilon squared log N over K. Yeah. And the proof is the probabilistic method. So again, you just take your n vertices on the left, and then what you do on the right is you just break up, for this setting of parameters, you just break up the right-hand side into little subblobs. where you have D subblobs, each with M over D vertices. And then you just pick a totally random graph. Each guy on the left has one neighbor chosen at random in each subblob. So one random neighbor here, one random neighbor here, one random neighbor here. Same thing here. One random neighbor here, one random neighbor here, one random neighbor here. And then you just prove that it has the property you want with high probability by a union bound. You look at all possible subsets on the left of size k, there are n choose k of them. You say with high probability, this subset doesn't have too much overlap if things are random, and then you union bound over all of them. Okay, so that's in terms of existence. People don't know how to construct such a graph deterministically that has this property. Okay, we just know that, you know, we can pick them. We know how to get graphs like that have that property randomly by just randomly picking a graph. It'll have it with high probability, although we don't know how to check that it has it. We just hope that it has it because it does with high probability. But if you want a deterministic construction, that's a major open problem in pseudo-randomness, is like constructing an explicit expander graph that has such good parameters. We don't know how to do that. Okay, good. So that's what an expander is. So what does that have to do with us? Theorem. If pi is the adjacency matrix of an expander with parameters, let's say specifically with, you know, k being like O of the sparsity. Sorry, I guess the k that you're going to choose in the definition of expander is going to be like O of the k that you use for sparsity. Can recover x tilde from pi x such that you're not going to get an L2 L1 guarantee. You're going to get something like an L1 L1 guarantee, such that x minus x tilde L1 norm is at most big O of 1, so some constant times x tilde k L1 norm. So you get an L1 L1 guarantee. And in fact, it's possible to make this be even like 1 plus epsilon. And that was due to Indyk and Ruzic in 2008. This was an iterative algorithm. And in fact, you can even achieve this thing here with basis pursuit. Okay. But again, there are also iterative algorithms that make it faster, that are faster than solving basis pursuit. So I mean, we only have 5 minutes left, so I'm not going to show you the proof of this. But it's just, you know, it's a totally different way. It looks very different from what we've been talking about before in terms of, what do we say? We said you can get an RIP matrix using JL. You can get it from fast JL. You can get it from incoherent matrices. So this is just totally different. And in fact, the adjacency matrix of an expander is not actually going to be RIP in the definition that I gave you earlier. It's going to be what's called RIP1. RIP1 means I preserve the norm, the L1 norm of any k-sparse vector, as opposed to the L2 norm. So you can show that. You can show that the adjacency matrix of an expander with the right parameters satisfies RIP1. It preserves the L1 norm of k-sparse vectors. And you can also show the converse. You can show that if you have a 0-1 matrix that satisfies RIP1, and by the way, you should, you know, in order to get RIP1, you have to normalize by the degree, but it's some universal normalizing constant. On the flip side, if you have a matrix where all the entries are either 0 or the same positive number, like 1 over D, you can show that if it has RIP1, it must be, you know, it must represent the adjacency matrix of an expander. So these are equivalent notions. Unfortunately, you actually can't prove black box that RAP1 implies basis pursuit works. That's actually false. You can come up with a counterexample of a matrix that has RAP1, but basis pursuit doesn't work with that matrix. This is an example of Michael Cohen from a few years ago. But if you use the fact that if you open the abstraction and say not only is it RAP1, but it's the adjacency matrix of an expander, you can use that property to analyze basis pursuit and argue that it gives you this kind of guarantee that I circled in red. Okay. Any other questions? Okay. And yeah, I guess maybe just one last thing I'll leave you with. This is unrelated, but for the many of you who said you hadn't heard of expanders before, expander, I mean, an intuitive way to think about these are combinatorial expanders. There's also something called spectral expanders, but they're actually related via something called Cheever's inequality. Well, the thing to have in mind when someone talks about expanders is an expander is a graph that doesn't have any sparse cuts. What do I mean by that? So you can define the sparsity of a cut, or the conductance, let's say, the conductance of a cut. Let's call it phi in the graph of S. The definition of that is just, this is what's called the boundary of S. Divided by the minimum of the volume of S and the volume of S bar. So what does this mean? The volume of a set is just defined to be the sum over X in A of the degree of X. So what it's saying, so, you know, expanders are graphs where phi of S is large for all small s. So what you don't want to have is, you don't want to have a situation where, so let's look at graph, let's look at some big graph. Let's cut off a small piece. So right, there's some edges here. There's some edges here. There are also some edges that cross the boundary. So the edges that cross the boundary okay. Let's say this is S and this is S bar. So imagine that S is the smaller side of the cut, right? Meaning that if you look at the min, here, S is the smaller side. So vol S has fewer edges that are adjacent, that are incident upon S. So what it's saying is the majority of the edges that are incident upon S are actually the yellow edges. It's, to be an expander means that there are few black edges on the S side of the cut. Most edges on the S side are yellow. Okay. It means most of the edges actually leave S. They don't stay inside S. It's related to spectral considerations because it's also related to the mixing time of random walks. So for example, imagine that you had a situation where here's S, there's a lot of edges in here, and it has one edge that leaves it to some much bigger region. Imagine that you did a random walk in the graph that started at some vertex in S. It's probably going to get stuck following all these black edges for a while before it finally crosses over this yellow edge. So we say that kind of that cut right here that separates S from S bar is an impediment to the random walk mixing quickly. So you want to say that there are no there are no such impediments. There are no cuts that are very sparse, that have very few edges crossing the cut. If that happens, it's not good. It doesn't, random walks don't mix quickly. So I mean, that's another so, related definition to expanders. That's the definition of what's called a spectral expander, which you can show has a connection to the definition that we talked about. But anyway, that's enough of an aside. I think we're definitely out of time now. Let me stop the recording and ask, are there any final questions?